Alright, so let's talk about binary search. So first, what's binary search? We all know this already when you use the phone book. If I'm looking for David, am I going to go from the first page? Second, Anthony, Adams, Abdullah, not yet, right? Bobby, Kelly, David. It's going to take some time, right? Why don't we just actually flip into the middle, somewhere in the middle top or somehow, right? So we get into the middle, and we see that we get into L. D should be on the first half, so we flip it to the first half, right? And then we said, oh, we got to D, so we found David. So we search into halfway every time, so that's why it's binary search, right? So let's say, for example, I have a list. I'm looking for a bat. I'm looking for a bat, and I went to see in the middle, dog, and B is, this is an order list. It might be sorted, right? For binary search, that's the recursive that has to be sorted. Precondition, the list might be sorted. Now B, get in the middle of the top half. Chicken. B should be another top half, which is in the middle. We got cat. We don't find it, then return. We're not having bat in the list, which is faster, right? 1, 2, 3, 4. Instead of searching 10 times and say you cannot find bat. Look at if the length of the list is 10. By using linear search, worst case is 10, right? Worst case for binary search is just 4. If you have the length as 100, linear is 100, binary search is 7, 1,000, 1,010, 10,000, 10,000, and 14. You see, if the list is very big, you only spend 14 instead of 10,000. So you reduce your efficiency in half. More than half in this case. We call efficiency of log n. So now we're going to look at, come back to recursive, right? We're going to use recursion to do this. So we're going to say recursive binary search. How are we going to write this using recursive? So first, think recursively means you have to look at what are the cases and what's the best case. Right, so first we gotta say case 1, if the key is less than the middle elements, recursively search for the key in the first half. Case 2, if the key is equals to the middle, the search ends. We match. Case 3, if the key is greater than the middle, recursively search for the key in the second half. So those are 3 cases, right? So we're going to write those cases. So we're going to use the recursive binary search, right? Passing the list and the key. And we're going to use the method, recursive helper method, right? Which is passing the index low and high. So first, low is going to be 0, high is going to be the length minus 1, always like that. And pass that right into the recursive binary search helper method right there. And this helper method is going to have the cases if low greater than high. Actually, this is actually we search and we not finding anything. When it's get low greater than high, the case that there's no such element in the list, right? So it's return minus low minus 1. Like, for example, if the list is 0, right? High is also 0. Length is 0, so it's going to give you high is equals to minus 1. And 0 greater than minus 1. So it's going to be returns minus 1 back. Right. So when it's negative, meaning that there's no such elements on the list. Now we start to look at our cases here. We're going to jump into the middle. So we're going to say mid equals to low plus high divided by 2. Right. So let's look at, for example, we want to find dog. Right. So 0 plus 10 divided by 2, we get 5. Right. So mid is 5. So if key less than key, we said dog. Dog less than list mid. No, it's actually equals. So we found return mid. Done, right? But if you're looking for cat, so if you're looking for cat less than dog, right? So it's going to return the same list with a key cat, and low index is still 0, right? But first half going to be mid minus 1. Then it's going to recursively call itself, do it this over and over again until it reaches cat. But if you're looking for something like greater than dog, elephant, so it's going to keep doing key, which is else case here, right? Key is greater than the list mid, which is else. That's why I didn't do if we could too. Then it's going to call the change your mid, like mid plus 1, and high stay the same because that's second half, and recursively call itself until you found it. And this is the algorithms for recursively binary search. Okay. This is another example. If you want to find the size of the directory. So it said recursive methods are efficient for solving problems with recursive structures. So this section presents a problem that is difficult to solve without using recursion. You may see before we can actually do iterative to solve those problems. Even recursive binary search, we can do recursive too. But let's think about this problem. The problem is to find the size of a directory. The size of a directory is the sum of the sizes of all files in the directory. So a directory D may contain subdirectories. Supports a directory contains files F1 to Fm. And subdirectory also have D1 to Dn. And you know, in the subdirectory itself can contain small files too. How would you find the size of the directories? Recursive, right? Use recursive. We said the size of the directory can be defined recursively. Think recursively by find the size of each file and the size of the directories, right? Sum them all up. So this is just like your method already, right? When you do the sum, right? So two methods that you need, right? The length method returns the size of a file. And the list files method returns an array of file objects under a directory, right? So let's look at the program. So we said this is a new file directory. So this is pretty much just create a new file type. And this pass in get size. So get size is going to be the one who calculates the size. So let's look at get size. So get size, take the files and initialize size to zeros. If we know that file has the method is directory, that means if it is the directory of file, right? If it's not directory, so it's going to else. Pretty much get the length of the file and accumulating to the size. If it is the directory, then you're going to call list all the files. It's going to return an array of files in that directory out. And inside, we're going to have to find the size of the files again by call get size, but the array can have more than one file inside, so we have to put the loops. Right, starting from zeros, right, list index to the end, I++. So n pretty much when I less than the size of the files here, and accumulating the size here. And we want to make sure one thing, that in case that it is an empty folder, then it should be returns null. We only do this when file is not equal to null, not an empty folder. So pretty much we use recursive to help here, right? So this is iterative with loops to get everything inside the folder, right? Get all the files inside the folder. But if it's directory every time, then we do this. If not, we accumulating the size. And you may see very simple by using recursive and easy to read. So that's the benefit of recursive. Another case study is the Tower of Hanoi. So this is a good example of using recursive to solve the problem, because you cannot use recursive to solve this problem. You cannot really not use recursive to solve this problem. That's what I said. So what's Tower of Hanoi? So that's a rules here. The game is you try to move all the disks from peg A. Right? This is a tower A, tower B, tower C. I'm going to call peg A, peg B, peg C. Right? You move them all to destination, which is C, by having the auxiliary B pegged, that you can always put, like if I want to move this one to this C, I can, because the rule said whenever you move, when you stack, the smaller disk always has to go on the top of the bigger disk. Like if I move 1 to C, 2 to C, then against the rules, right? Because 2 is bigger than 1. That's why I have to use the auxiliary to help by putting 1 to B first, and then 2 to C, and then have to move B back to A, right? Or actually have to move B back to C, and then I can move here 3 back to B, right? And then I can start to move 1 back to B, right? And then move C back to A. And then 1 back to A, right? I keep stacking, then I can move that bigger one to